Going to be talking about what's called a related rates question. So related rates, I just want you to really focus on that rates word. So if you remember, rates in math are like our slope, our rates of change. So like our average rate of change, our instantaneous rate of change. Okay. All of our derivative units, we've been finding rates. We've been finding the derivative, which is that instantaneous rate of change. Okay. When we talk about related rates, we're talking about a situation where we have multiple things that are changing that are related to each other. So think about if I was filling a pool with water, okay, the volume of the pool is changing would be related to the rate, the height of the water in the pool is changing. You know, those are two similar things. They're both going to be influenced by the rate of me pouring water in. So that's what we mean by related rates. And we can use calculus to kind of discover all of these different rates and solve for them and find out more information about them within context of certain problems. But we got to start all the way down at the basics. And the first is we have to be able to take kind of words and translate it into calculus notation. Okay, so number 1 through 4, we're just going to be translating the sentences into a calculus notation. Okay, so the volume of a cylinder is increasing at a rate of 5 cubic meters per second. Okay, so my rate is 5 cubic meters per second. Okay, and then it is the volume of a cylinder is increasing. Okay, so volume is what's changing over some measure of time, specifically cubic meters in volume is changing over a certain amount of seconds. So the way that we're going to write this is dV dt. Okay, so the rate of change of the volume over the rate of change of time. So that dV over dt, that whole thing is the rate of change of the volume over time. Okay, so the rate of change of the volume with respect to time is equal to, and then they told us 5 cubic meters per second. So 5 meters cubed per second. Okay, and it is increasing, so it should be a positive rate because we're adding in 5 meters cubed every second. Okay. So number 2, the height of the water in the rectangular pool is decreasing at a rate of 2 inches per minute. So height is what's changing over some time. Okay, so we want to say dH dt for the rate of change of height with respect to time is equal to, and the height is decreasing at a rate of 2 inches per minute. So we want to do -2 and then inches per minute. Okay. At rush hour, the number of vehicles going through the toll booth is increasing at a rate of 82 cars per hour. Okay. So this one's a little weird, but I'll do maybe dC dt for cars. Okay. So dC dt is increasing. So 82 cars per hour. And then last but not least, the air is escaping a spherical balloon at the rate of 15 cubic centimeters per second. Okay, so air is escaping, so that means the volume would be decreasing, okay, from my spherical balloon. So dV dt for volume would be equal to -15 centimeters cubed per second. Okay. So that is how we kind of translate these words, which is very important because these are sentences that could come up in a related rates question, how we translate these words into actual calculus notation, that derivative, okay? Because remember, a derivative is just slope, and slope is just a rate of change. So for the following formulas, we're going to take the derivatives with respect to time. Remember to consider which variables change with respect to time before you take the derivatives, okay? So what this means is we're going to be deriving all of these equations with respect to time, which means we're deriving with respect to the variable t. Just like normally with our derivatives, we derive with respect to x. So that's why we have like our dy over dx. Okay. When we derive with respect to time, we're going to have d, whatever variable we're deriving, over dt with respect to time. Okay. With respect to that variable t. Okay. Now, any variable we derive that is not t just like in implicit differentiation, when we derive that variable, we're going to multiply by d that variable over dt. Okay, let's see it in action. So on number 5, we have the volume of a cube. V is equal to s cubed. So I'm going to derive both sides of the equation. So the derivative of v, okay, is just 1, because just like if I derived x, x would become 1. So if I derive v, it would become 1. But then I multiply by the derivative of v with respect to time. So I multiply by dv over dt. So that'd be equal to, what would the derivative of s cubed be? Well, that's a power rule, so 3s squared. And then I multiply by, because I derived a variable that was not t, ds dt, because I derived s, so I get ds dt. Okay? And to write it just a little bit simpler, because I don't really need that extra 1, this is really just dv dt is equal to 3s squared ds dt. So to kind of read this, translate our calculus equation into words, instead of the other way like we were doing other words, the rate of change of the volume with respect to time is equal to 3 times the side squareds times the rate of change of a side with respect to time. Okay, so see how we have these two different rates in the equation, and they're related by this equation, hence the name related rates. So all of these equations, we're going to be finding related rates derivatives. Okay, I'm going to do a couple more examples and then pause the video, because then I'm just going to show you all the rest of the answers. So I'm going to do about 3 or 4 more of these, and then pause it, try the rest on your own, and then you can check your work here in a bit. Okay, so let's look at another one. So area of a rectangle. So we have A is equal to length times width. Okay, so I have 3 different variables here. So when I'm deriving, I have to consider that all those different variables are like their own separate functions. Okay, so the derivative of area would just be dA over dt, or 1 times dA over dt, equal to the derivative of length times width. Well, those are 2 different functions being multiplied. So what rule do I have to use? I have to use product rule. So the derivative of length would be dl dt. Derivative of w would be dw dt. And then I would cross multiply like I always do for my product rule. So this becomes length times dw dt plus width times dl dt. Okay, so just like with implicit, if we have 2 different variables being multiplied together, we have to do product rules. Let's look at another one. Let's look at number 8, volume of a sphere. Okay, volume is equal to 4/3 pi r cubed. Okay, so volume derivative is dv over dt equal to 4/3 and pi. That's all just a constant. So the only thing I'm actually deriving is that r cubed. So I get 4/3 pi 3r squared times dr dt. And then that 3 and that 3 cancels out. So this is really just dv over dt is equal to 4 pi r squared. Oh, sorry, dr dt. Don't want to forget our dr dt. Okay. One last one. We'll look at one that's a little harder, like 12. Volume of a cone. We have volume is equal to 1/3 pi r squared times h. Okay. So just like normal, our volume is dv dt. And if you notice, y'all, all of these are equations for various shapes, and most of them have just like volume, area, surface area, circumference, perimeter by themselves on one side of the equation. So really, that's just going to be your easy derivative. It's the right side of the equation that's typically going to be a little bit more work, but it just kind of depends. Okay, so dv dt is equal to, okay, now in this big mess of stuff, I have r squared times h. Okay, so this is a product rule to make it a little bit easier. Okay, let's split it up. I'm going to give all of my constants to r squared. So my first piece is going to be 1/3 pi r squared. My second piece is going to be h for my second function. So the derivative of 1/3 pi r squared would be 2/3 pi r dr dt. Derivative h is just dh dt. And then we cross multiply. Boom and boom. So 1/3 pi r squared times dh dt plus 2/3 pi r dr dt times h. So 2/3 pi r h dr dt. I always like to write the related rate at the end of whatever term, just so it's easier to see it because it's kind of the big old messy fraction like that. And that would be our answer. Okay, so a little messy, but same sort of deal. You just have to do that practical before you finish it out. Okay, go ahead and finish the rest of these so you can pause me, and then we'll move on to something else here in a second. Work real quick. Kind of zoomed out here so you can see all of them. So just go over 7 ds dt is equal to 2 pi r dh dt plus 2 pi h dr dt. Another one we didn't do, the side lengths of a triangle, 2x dx dt plus 2y dy dt equals 0. Volume of a cylinder, dv dt is equal to pi r squared dh dt plus 2 pi r h dr dt. Area of a circle, dA dt is equal to 2 pi r dr dt. Circumference of a circle, dc dt is equal to 2 pi dr dt. And perimeter of a square, dp dt is equal to just 4 times ds dt, which I like the perimeter of a square one because it makes so much sense to me, that the rate the perimeter is changing would equal to 4 times the rate the sides of the square is changing. So if I have 4 sides of my square, and all 4 of my sides of my square changing at the same rate, which they should be, or else they won't be a square, then my perimeter will be changing at that same exact rate times 4. So I just like that equation because it makes so much sense in the brain. All right, so this is all fine and good to kind of as some background for us to be able to do a related rates question, but now we need to actually be able to solve a real true related rates question. Okay. So I've given you a couple of steps. Okay, the first one, because it's a real world situation, really, they're all so very different. The first step you should always do is draw a diagram, draw a picture, something to represent what is happening. The second step is my favorite step, and hopefully the step that you never forget, and that is to fill in Fwiggy, or as me and Miss Reichert say, to get Fwiggy with it. Okay. So Fwiggy stands for find, when, given, and equation. And I'll talk a little bit more about that when we get to an actual problem. Then our third step is to find the derivative of our equation using that related rates method that we just did up above. And then for step 4, we're going to substitute all the stuff in we got with Fwiggy and solve for what we're trying to find, what we have in our find step. Okay, so let's look at an example. So number 1, the top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? Okay, so step number 1, we want to draw a picture. So we have a nice little wall with our ground. Nice little ladder. Okay, our ladder is 25 feet. And it's sliding down a vertical wall at a constant rate of 3 feet per minute. Notice how I made that negative, because if it's sliding down the wall, then that wall side should be decreasing in length. Okay. When the top of the ladder is 7 feet from the ground, so that means when this same side is 7 feet, okay, what is the rate of change of the distance between the bottom of the ladder and the wall? So I want to know this change right here, which notice that I did point outwards, because if my ladder is falling down, it would only make sense for the other side to be increasing in size. Okay, So I want to know that. That's what I don't know. Okay. Before we can get into our Fwiggy, what kind of shape is this? Well, hopefully you can see it right away, but it is a right triangle. Okay. And just to give a little bit more definition to our right triangle, it makes sense to name it appropriately so we can kind of know what sides we're working with. So A, B, and C are typically the variables you give for sides of a triangle. Okay. And now we should be good. We got a really great diagram. Okay. So number 2, we're going to set up our Fwiggy. Okay. So the first step in Fwiggy is our find. So what are they trying to get us to find? So they want us to find the rate of change of the distance between the bottom of the ladder and the wall. So that's this change inside A, which we'd write the change inside A over time as dA dt equals what? Okay, so that's what they want us to find. When do they want us to find it? That's our W in Fwiggy. So when do they want us to find it? When the top of the ladder is 7 feet from the ground. So when which side, B, is equal to 7 feet. Okay. Given, G, stands for any other given information in the problem. Well, they tell us that C is equal to 25. Okay. They tell us that dB dt is equal to negative 3 feet per minute. Okay. Any other given information? No. We could solve for something else, which you'll probably see is needed. I have B, I have C, but I don't have the length of side A. And it is a right triangle. And not just any right triangle, but it is a perfect trinomial, not perfect trinomial, Pythagorean triple. Sorry, getting my math terms mixed up. So this Pythagorean triple, this specific Pythagorean triple, is 7, 24, 25. So I could find that last side A, as my Pythagorean triple. So A is equal to 24. Okay, if you did not know that, we could also use the equation we're going to find for our part E. So Fwiggy FWG, find when given equation. So we want an equation that's going to relate the situation together. Well, the only equation that relates sides of a right triangle together is the Pythagorean theorem. So E is equal to A squared plus B squared equals C squared. Okay. So if you didn't know A, if you didn't know 7, 24, 25, we could always use this equation to just solve for A really quick. Okay. So that's step 2. Step 3 is I want to go ahead and derive my equation. Now, the one thing that we always have to check for before we derive a related rates equation is we have to check for if we have any variables that are not changing in the problem. So let's look at our problem. The length of the wall between the ladder and the ground, that wall is changing. The length between the ladder and the wall, that length is changing. But is the length of our ladder ever changing? No, it's always a 25-foot ladder. So what I can do is before I derive it in step 3, I can plug in for C because C is not a variable that's changing, which means I don't want to get like a dC dt because there's no change in C. So I don't want to get a rate of change of C because that doesn't exist. C isn't changing. So for step 3, we have our equation, A squared plus B squared equals 25 squared. So I just went ahead and plugged in for C real quick. Okay. Now I'm not even going to worry about squaring 25 because I'm about to derive this equation. What's going to happen to a constant when we derive it? Just going to go away, which is really awesome. Okay. So the derivative of this using our related rate style would be 2a dA dt plus 2b dB dt equal to just 0. Okay. And that's step 3. So step 4, our final step, is just to plug in all of our Fwiggy and solve for our find. So I'm going to plug in everything except dA dt and then just solve for dA dt. So we have step 4. So we have 2 times A, which is 24, times dA dt, which we don't know, plus 2 times 7 times dB dt, which is negative 3, equals 0. So this is 48 dA dt plus 2 times 7 is 14 times negative 3 is 42. So not plus, it would be negative 42. Equals 0. So 48 dA dt is equal to 42 dA dt equals 42 divided by 48. So dA dt is equal to, both those are divisible by 6, which would be 7/8. And then because it's a related rates problem, it's a real world problem, I want to add in units. So our unit should be feet per minute. And that would be my answer. Okay. So some things to check out. Your related rate should make sense. Okay. So we got a positive answer at the end. So it's saying in our situation, if our ladder is falling down 3 feet per minute on side B, then side A is going to be increasing by 7/8 of a foot per minute. Okay. That makes relative sense. Decreasing on one side, increasing on the other side. Okay. So always check your number, your answer should make sense. If it doesn't make sense, then you probably did something wrong. Okay, these notes are getting long, so we're going to do one more. Okay, I don't want to keep y'all here forever, but a pebble is dropped into a calm pond, okay, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 feet per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, so step 1, draw our picture. So we got a pond. And yes, it is concentric circles, so I am going to make a nice pretty circle for my pond. That's not the best circle. We're going to try again. There we go. That's better. Okay, so we have a pond with rocks being dropped into the middle, or pebbles, creating little circles as we go out. Okay, this radius right here is increasing at a rate of 1 feet per second. Okay, then we want to know specifically when r is equal to 4. At what rate is the total area of the water changing? So at what rate is this changing? Okay. See, any other information? No. Okay, so now we can do step 2. We can get flicky with it. Okay. So step 2, first of all, is find. What are we trying to find? So they want us to find the rate when the total area of the disturbed water is changing. So the rate of the area would be dA dt. When do they want us to find it? When the radius is 4. So notice how I'm just looking for those key words in this problem. When 4 feet is equal to r. Okay, given information. Okay, the only other thing we're given is the rate of change of radius. So dr dt is equal to 1 feet per second. Okay, we're not given the area. We could find the area, but I don't think we're going to need to find the area. So let's hold off on finding the area of the equation when the radius is 4. Okay, and then last but not least, we do need an equation. Okay, so we're relating radius and area of circles, so we need an area of a circle. Okay, so area of a circle, A is equal to pi r squared. Okay. So then from there, step 3, we're going to take our derivative. Is there anything in this question that is not changing before we take our derivative? Well, our area is changing because we want the rate of change of the area, and our radius is changing, okay, because they told us the radius is changing. So everything's changing, so we're not going to plug in anything before, so we're just going to derive it like normal. So A is equal to pi r squared, which means dA dt is equal to 2 pi r dr dt. So that is our equation. And then step 4, we're just plugging in all of our givens. and solving for our find. So dA dt dA dt is equal to 2 pi times r, which would be 4, and dr dt, which would be 1. So dA dt is equal to 2 times 4 times 1 is just 8 pi. And then our units area is feet squared per second. And that would be it. Okay, so that is related rates in a nutshell. I'll go over another example in class. But the big thing with related rates, y'all, is just making sure you're deriving that with respect to t, and drawing the fixture and making sure you have all that information. It's going to make your life a lot easier with these questions.